we're going to now use our calculators and some graphing techniques to approximate zeros of polynomial functions. Taking a look at example 8, it tells us to use a graphing utility to approximate the real zeros of a polynomial and give their multiplicities, if any, and determine how many complex zeros the polynomial may have. So starting off, we have this beautiful function, which we're going to go into y equals, and I'm going to use my math type print on my calculator to get this entered in. So I'm going to hit alpha y equals, and I'm going to choose number 1, and I'm going to put in 1/4 x to the third, and then plus 3/8. So now I'm going to do another fraction, so I'm going to hit alpha y equals number 1, 3/8 x squared minus 4x plus 4.5. And I'm just going to hit graph and see what I have. Okay, so we notice right away that we have one of our zeros crossing, or as in a place where we cross from a negative to a positive. So we have an odd multiplicity on this one. And then we have another zero where we're bouncing off the x-axis. So this one has an even multiplicity. Also notice that our highest degree is a 3. So this is a third degree polynomial. So we can have at most 3 zeros. So let's go find those zeros, and then we can talk about the possible complex zeros that this polynomial has. So I'm going to go into my calculate menu. So I'm going to hit second trace, and I'm going to find a 0. And in this case, the first one is pretty straightforward, as we've done this many times. It wants to know our left bound and our right bound. So what we have to do is we have to get our spider, or our cursor, down here to the left of the intersection. And in this case, if we come in from the left of the function, it's going to be below the x-axis. So I'm going to get it as close to that 0 as possible and hit enter. And then I'm going to move to the right bound, which means just hit this right cursor to where we're on the other side of the x-axis and hit enter. And then my guess, and my 0 is x equals a negative 5.223, just approximating the 3 decimal places. And it has an odd multiplicity. Now let's go get our other one. And this one's a little bit more, but it's not as much below and above the x-axis, because this particular 0 bounces off of the x-axis, or the graph does, at this 0. We're going to hit second trace 0, number 2. And we're going to have to cursor over where our spider is to the left of where it bounces off that x-axis. So about right there. And hit enter. And then cursor to the right of where it bounces off the x-axis. And our other 0 is at x equals 2. And it has an even multiplicity. So now we can write or talk about the multiplicities. Since we have a maximum of power 3, this one has a multiplicity of 2. And the other one must have a multiplicity of 1. Because the multiplicity, the maximum that the multiplicities can be, happens when you add up the multiplicities, and they cannot be larger than the degree of the polynomial. So we have a multiplicity total of 3, 1 and 2, and that matches our degree, so there are no complex zeros. It's when the multiplicity and you add them together, and it ends up being less than the degree of the polynomial, that you start suspecting there are complex zeros occurring. Let's take a look at part B. Entering in our g of x function. Notice once again it's a polynomial of degree 4. Always notice the degree of the polynomial and have it entered into y equals and hit graph. We have an interesting looking function. Now, notice that it crosses the x-axis only twice, and both of those times it goes from a negative, in this case, to a positive. It changes signs, and then from a positive to a negative. So both the times that it hits that x-axis, the function changes signs on the other side, which means that we're looking at an odd multiplicity. So let's start off by finding our intersections here, these x-intercepts, and hit second, calculate, number 2. And it starts up here on the y-intercept because that's just the way the TI-84 always starts off when you begin these. And I'm going to go back and forth, and I want you to notice as I'm going back and forth, this y value. Over here is negative, and that's as close as I can get to that intercept on the negative side. And then when I hit it one more time, it turns to a positive. So those are the two closest values that this calculator can give me to start off with without zooming. And I'm now going to answer the question of left bound, right bound. So coming from the left, it's negative, and then it changes to a positive. So my left bound is going to have the negative y, and my right bound would have the positive y, and hit enter, and my 0 is x equals a negative 1.380, and it has an odd multiplicity. And then let's go get that other 0, second 0, number 2. And we notice that if I'm tracing from the left, I go from a positive to a negative. So watch those numbers. That's still positive. I'm going to drop that as my left bound. And then when I hit that cursor one more time, my y changes to a negative. So I hit enter. And there's my guess. So we get x equals 2.7603018. And that's an odd multiplicity as well. Now at this point, we have an interesting conundrum, because one of these could be a cubic multiplicity, and the other one would have a multiplicity of 1. And we honestly don't know. Or both of them could just be a multiplicity of 1, and we have a possibility of 2 complex zeros. Now, I am guessing, because of this right here, the way it turns around, I'm guessing that that is telling me that our zeros are going to work out to a 3 and a 1. But I don't know for sure without further exploration of the function. So I'm going to say that these are odd multiplicities. It could be either a multiplicity of 1 or a multiplicity of 3. And this one could be a multiplicity of 3 or a multiplicity of 1. So we're either going to have these two going together or these two going together to give me that degree. Or possibly we could have these two happening, which means that we have the possibility of 2 complex zeros. But once again, we won't know unless we go more in depth into this problem. Let's take a look at C now. On C, we have 1/2 x to the fourth degree polynomial that then has a descending order all the way across. A degree is not missed from x to the fourth to x to the 0. I'm going to, instead of using my pretty print, I'm going to say 1/2 is the same thing as 0.5. So I'm just going to say 0.5 x to the fourth minus 3x cubed minus 2x squared plus 11x plus 5. And hit graph and see what we have. Now when we take a look at this, notice it crosses the x-axis 1, 2, 3, 4 times. So that means that this degree 4, it has 4 real zeros. And all of them have a multiplicity of 1. Because that's the maximum that we can have. And since they all cross the x-axis, none of them are bouncing off the x-axis, we know there's not an even multiplicity happening. And if we try to say one of the odd multiplicities was something like 3, there's no way it could happen, because we have 4 real zeros, and that's the maximum number of zeros that we can have for a 4th degree polynomial. So if we wanted to find these, it's just going to be a process of hitting second trace 0. There we go. So I get x equals negative 1.73. You notice over here that 1e negative 12, that means it's really, really close to 0. So I'm going to take that and be happy with it. And then I'm going to get this next 0 right here. And it's at negative 0.44. And then I'm going to get this 0, second trace number 2. And it's just a matter of moving around your graph. And I have x equals 2.16. And then one more 0 to go, second trace number 2. Same button presses. Whoa, that guy moved fast, didn't it? So that's as close as I can get to it on my calculator, and my calculator estimates that's my other 0.